Hello, my name is Yahya Al-Hazza from King Abdulaziz University, Nuclear Engineering Department. Today we are going to talk about our project, which is building gas-filled detectors. Our project comprises of two detectors built with different methodology as a phase one of the research. The first detector uses more conventional ways and operates as a counter on a Geiger-Muller region, which is very high voltages. The other one uses more modern material, 3D printed material, and operates on lower voltages, which called ionization region. The end goal is to compare the two and uses the best techniques to combine these two detectors into one gas-filled detector that can be used in different regions as a spectroscoper or as a counter as well.
Hello everyone, my name is Rayyan Ford, a medical physics student in King Abdulaziz University Faculty of Engineering, Nuclear Department. The first design is a simple cylindrical GM detector that made of stainless steel 304 material, while the other design is a spherical ion chamber that made of 3D printed material called carbon-based conductive PLA. The stainless steel 304 is an excellent conductive material and it's suitable for the GM cylindrical design, while the 3D printing material needed a modified 3D printer with a nozzle temperature 235 degrees Celsius. The resolution for printing is 0.5 millimeter and the volume resistivity is 30 ohm centimeter for the XY axis and 115 ohm centimeter for the Z axis.
As for the designs, we start with the ion chamber. This particular design of the ion chamber is cited from KITH Royal Institute of Technology in Sweden. Modifications have been made to suit our research. Different conductive material have been used. In this particular drawing, we find that it is a section view of the detector. The detector comprises of two materials. Conductive materials, which are the anode, the cathode, and the guard, and an insulation that is between the anode and the guard, and between the cathode and the guard. The cathode is a radius of 40 millimeters. Inside this cathode, multiple tubes that are assembled by pressing. To assemble it in this way, we needed to take into consideration the thermal expansion when it's printed, thus a space between each tube of 0.25. Inside the cathode, different multiplication regions can be created, one between the anode and the cathode, one between the guard and the cathode, or both of them, one between the anode and the guard, and one between the guard and the cathode. It should be mentioned that this particular model uses air only as a gas, and it operates on multiple voltages, taking into consideration a very low current to prevent heat expansion. As for the Geiger-Muller counter, the detector has much simpler design. We have a cathode of a conductive material, and we have an anode of the same conductive material, and in between is the detection volume, the anode of 5 millimeter diameter, and the cathode inside is of 19.9 millimeter in diameter. Also, we have a three-way cannula to allow for gas filling inside the detector, and finally we have a glass window to allow beta and gamma rays to enter the detection volume much easier. To understand the operation regions for such geometry, the reference detector was used to characterize the operation regions empirically and generated data that characterizes the plateau in which the Geiger-Müller region will start on. To optimize the detector for better collection, simulations were used to understand how to enhance the electric field generated from the applied voltage on the anode. One was made for the 1.5 millimeter anode, another was made for 5 millimeter anode, and the final one for an 8 millimeter anode.
The GM circuit is very simple. It's made of three main components: the source resistance, the ground resistance, and the capacitance. The source resistance is responsible for blocking the flow current inside the circuit, while the ground resistance and the capacitance is responsible for charging and discharging time.
I am Muller Counter from King Abdulaziz University, Department of Nuclear Engineering, and today I will discuss the phase 1 of our project, making ionization chamber detector. In our detector, we are making our detector from 3D printing material, and we have operated our detector in ionization region. So in our circuit, we have a resistor that blocks any unwanted current. Also, we have a resistor that are parallel to capacitor. That capacitor will collect our electron signal and will control, this system will control a decay time of our detector. In order to increase our signal, we have decided to use op amplifier, or what we call LM741, that will increase our signal from 150 millivolt up to 1 volt. It should be mentioned that the circuit design is independent from the research done by Keith Royal Institute of Technology in Sweden.